and terminal Pleistocene. Actually, how do I get that in the slideshow? Please excuse our technical difficulties.
Act 5.
So the goals of this study were fourfold. First, I was examining local pollen history. I was utilizing that to create a proxy for climate. I was examining how well this particular site conformed to the greater region. And I was looking for any local quirks or anomalies that didn't fit with the region. During this defense, we'll start with a brief description of the region. We'll talk about previous research, methods of pollen preparation and analysis, and then we'll get into the results and interpretation of those results. The sediment core in question was extracted from Lake Louise, Washington, which is in the area to the southeast of the Puget Sound. Lake Louise is a kettle lake. It's relatively small, and it's located in a north-south trending valley, which, as you can see, is not unusual in this part of the country. These valleys are so common because this area was buried at the end of the Pleistocene under a massive sheet of ice. To be specific, it was buried under the Puget lobe of the Cordilleran ice sheet, which advanced southward from Canada about 19,000 years ago, and then retreated around 16.6 thousand years ago. Dividing this region into various subsections, we get essentially three regions. Puget coastal rain shadow, with this extended piece that is treated like the Puget coastal rain shadow. It's got a similar climate and a similar pollen history, but is being affected by a different phenomenon. The southern Puget lowlands, and the Olympic west coast. There are also a couple of minor areas which will be discussed further later on. So the Puget coastal rain shadow is the driest area in the region. Lake Louise is to be found at the southern terminus, as the LL here. The southern Puget lowland is a good moderate indicator of the region. Pollen records from this part of the state tend to be a pretty good proxy for the region as a whole. It does show some really good evidence of early aridity. And the northern boundary is immediately adjacent to Lake Louise. Finally, the Olympic west coast. The Olympic west coast combines prevailing westerlies, which gather moisture from the Pacific, and a mountain chain, which causes the atmospheric content that has been gathered, the moisture that has been gathered, to rise, condense, and fall out. This leads to the heaviest precipitation in the region. Specifically, if the Puget coastal rain shadow is the driest, that actually just means that it is average compared to the rest of the United States. It gets about 3 feet of rain a year. The southern Puget lowlands get about 5 feet. And the Olympic west coast get slightly more than 1 J. Michael, or about 7 feet. So now, getting into previous research, there is a general trend that is observed among multiple pollen sites, which is at the terminal Pleistocene, records tended to be dominated by Pinus contorta, the lodgepole pine. It's generally very difficult to actually identify pollen down to the species level, but there wasn't a lot of other pine in the area, so contorta is mostly by inference. Then, 11 to 8,000 years ago, the pollen regime shifted to Ulmus rubra, red alder, to the Pseudotsuga menziesii, hard to pronounce, Douglas fir, and Pteridium, or fern. Finally, around 8 to 3,000 years ago, the record shifted again to Thuya plicata, which is a member of the Cupressaceae, and Tsuga heterodon. And in most cases, that's the end of the story. Well, that's a lot of pollen, but that doesn't really mean anything to most of us. So the interpretation behind it is that it was initially cold. 11 to 8,000 years ago, it recorded warming and drying. And 8 to 3,000 years ago, that changed to a cooling, moistening trend, which persists to the present day. I mentioned that the Puget coastal rain shadow was the driest area in the region. It also has the driest specific pollen site in the region, Manus mastodon site. This region actually recorded cactus pollen in the early Holocene. It also illustrates the importance of getting multiple pollen sites to get a good proxy for the region. In 1995, McLaughlin and Brubaker studied Cedar Swamp and Crocker Lake. They look reasonably different from one another on a macroscopic scale, as you can see, and their pollen records look somewhat different from one another. This is despite the fact that they are separated by only 3 kilometers. The southern Puget lowlands, as I mentioned, is a pretty good average for the region. It shows excellent evidence of early aridity, including the presence of xeric taxa such as artemisia or sagebrush. The Olympic West Coast, as I mentioned before, extremely high precipitation. It also had an interesting quirk in that transitions tend to be delayed here. So I mentioned that the first transition to a warming, drying climate happened between 11 and 8,000 years ago, depending on the site. Most of the 8,000 year transitions were here. Just because this area has extremely high precipitation, however, does not mean it has no charcoal, no fire. Washington has a highly seasonal climate of wet winters, dry summers. And so all that rain in the winter can, in many cases, just lead to a massive buildup of fuel for the summer. And in fact, in one site, Yahoo Lake, there is a high recorded charcoal abundance. We also have a couple of minor areas. The first of these is the Western Cascades. This is divided up into 2 sites. The northern one, studied by Kunar, records high moisture in the earliest Holocene. It also talks in a lot of detail about fire, which I'll get into later. The other site included 3 high-latitude ponds around Mount Rainier. The cores were very short, but while they only recorded about 6,000 years of data, they agree very well with the broader region. The other area, the other minor area, is the Olympic Highland. And this area is important because it shows at what point regional conformity ends. These sites were around 1,300 meters above sea level, and in contrast to the rest of the region, recorded a much lower amount of arboreal taxa, far fewer pinus and other trees, and far greater amount of time spent as alpine meadows. So now we're going to get into the methods for pollen preparation. And the first part of preparing pollen for microscopic analysis is to add lycopodium. The reason we do this is because it allows us to statistically determine the total number of grains in a slide within a reasonable margin of error without having to count every grain. And the way this works is that the number of grains counted divided by the total number of grains in a sample is equal to the number of lycopodium counted divided by the total number of lycopodium in a sample. And we know these three. So, as a simple example, let's say I counted 20 pollen grains, and I counted 10 lycopodium grains, and I know I've put in 100 lycopodium grains. Well, then the total number of pollen grains in our sample would be the number of grains counted times the total number of lycopodium divided by the amount of lycopodium I counted, or in this case, 200 grains. Please note that this example, in addition to being simplified, is far, far smaller than the numbers that are actually observed. After the lycopodium is added, the sample is immersed in water, a magnetic stir stick is added, and it is disaggregated. Then, HCl is added to remove carbonates, followed by immersion in hydrofluoric acid, HF, to remove silicates, and then without rinsing the sample, it's put back in HCl to prevent the silicates from recrystallizing. At this point, it's rinsed. Then it undergoes immersion in nitric acid, which allows continued disaggregation. Samples are then rinsed again and put into glacial or undiluted acetic acid. This step prepares samples for acetolysis. Acetolysis is the process through which we remove organic compounds that are not pollen. And if we allow the reaction to proceed to completion, it will destroy the pollen, but pollen is, as you may have guessed from all the previous stuff we've done to it, remarkably tough. So we start out by adding acetic anhydride and sulfuric acid to get the reaction going. And then we add glacial acetic after 90 seconds to terminate the reaction. The sample is then immersed in 5% potassium hydroxide to wash away the organic remnant. At this point, it's ready for staining and mounting. When one is counting pollen, one does it at a 400x magnification, counted to a minimum of 300 terrestrial grains per sample, and then abundance of each pollen type is counted as a percent of terrestrial grains. And by terrestrial grains, what I mainly mean is not ferns. Charcoal was also counted. I counted charcoal alongside lycopodium and counted until I reached 40 lycopodium and then recorded the amount of charcoal tallied during that distance. It's also counted at 400x. And I have to say, I really like this slide because this shows what it's like looking down a microscope much better than the crystal clear images that you've gotten of other pollen grains. Even after all the acids we've applied, there is still a bunch of stuff that we're not interested in. So after all that counting was done, it was amalgamated into a graph. Relative proportions of different pollen types were put in, and cluster analysis was performed. So here's the first part of that graph, dealing with conifers and other arboreal taxa, where the y-axis represents depth, with the top of the core at the top, and of course is also a proxy for time. The x-axes represent abundance of given taxa, so Pinus, Pseudotsuga, Tsuga, etc. The shaded areas represent pollen assemblage zones, and the red lines represent dates. The top date, 1863, was acquired using lead-210 dating. The middle, 2840 plus or minus 40, was acquired using radiocarbon. And the lowermost date, 7627 plus or minus 150, was acquired as Kepra from the eruption of Mount Mazama, which is now known as Crater Lake. The next part of the graph discusses the non-arboreal taxa. And as you can see, not a lot going on in the non-arboreal sections. Again, the y-axis is depth, the x-axes measure abundance, the boxes are zones, and the red lines are time. You can see that grass crops up periodically, and grass largely behaves similarly to thuya. We can also see some fern abundance early on, which we'll get into shortly. Finally, we get to the summation and statistics. So here you can see the arboreal sum, which indicates why the non-arboreal sum is not really considered a major part of this story. It never really dips below 80%. There's also ferns, other, which is the combination of those grains that were too damaged to identify, and those grains where an identification was not possible. Pediastrum is included, which is a type of algae, as is pollen concentration and charcoal concentration. So breaking this down zone by zone, zone 4, at the base of the column, and therefore oldest, has a high abundance of pine, which declines towards the end of the zone, a low abundance of Pseudotsuga, which increases towards the end of the zone, and a low abundance of Alnus rubra, which again increases towards the end of the zone. It also has the highest charcoal abundance of any of the 4 zones. In zone 3, you can see that Pinus has declined significantly. Pseudotsuga is reasonably high. Alnus is quite high. And charcoal abundance was very high here, but not quite as high as in zone 4. In zone 2, thuya becomes much more pronounced. Pseudotsuga increases. Tsuga increases. And Alnus rubra decreases. Pollen abundance and charcoal abundance are both low. You'll also notice these odd and very significant sized fluctuations occurring in zone 2. In zone 1, thuya declines, Pseudotsuga increases slightly, Tsuga remains roughly constant, and Alnus rubra increases. Pollen and charcoal abundance were both low again during this zone. So, what does that all mean? This being a geology presentation, a ternary diagram is considered mandatory. So to explain, at the lower left, we have Pinus, which is representative of cold conditions. At the top, and slightly cut off, we have Pseudotsuga, representative of warm conditions. And at the bottom right, we have thuya, representative of wet conditions. So for zone 4, we see cluster very much composed of pinus, representing a regime dominated by cold. And while it is very hard to follow these lines, you can sort of see that towards the end of zone 4, it's starting to warm up. Zone 3 records a warmer period, and you can see that it's starting to shift a little bit towards the wet, but still not very much, mostly a drier climate. Zone 2, you can see, has a wide dispersal. This is representative of that scattering I mentioned, of that fluctuation I mentioned. And it's alternating between warm and wet. And finally, Zone 1 is very much dominated by warm climate, by pseudotsuga. So what is the significance of this? The significance is threefold. In zones 4 and 3, findings largely corroborate previous studies. In zone 2, this unusual fluctuation was observed, which is not generally seen in other studies. In zone 1, most other studies actually don't record a zone 1 because they don't have enough samples to separate it out. But this particular study had a massive increase in sedimentation, which led to an increase in number of samples available. No study is perfect, this one included. The most prominent limitation of this study is that it does not have a carbon-14 date for the base of the core. A date was attempted, but unfortunately the sample was contaminated. Instead, we have a presumed date based on averaging of sedimentation and on glacial retreat. These two figures give us slightly different results, but they are very close to one another. Another problem is that no parkland was observed following glacial retreat. And this could be due to one of two reasons. It's possible that immediately following glacial retreat, conditions were still significantly disturbed to the point that sedimentation did not occur in significant quantities. And it's also possible that the transition from glaciated to pinus-dominated was a very rapid one. Observations of zone 4, as I mentioned earlier, high declining pinus, low but increasing pseudotsuga and ulmus rubra, suggesting a cold but warming time. There was a potential canopy opening observed by the increase in pteridium or fern in the middle of the zone. And this particular site had the most charcoal abundance. So while we aren't seeing xeric taxa, we're seeing a lot of fires, and we aren't seeing a lot of taxa that are more hydrophytic. So this can be interpreted as evidence of a dry climate. And this does largely conform with the region. Findings were that it was cold but warming. Some sites show evidence of aridity. Some actually are wet enough that they are classified as taiga, and generally high fire frequency. During zone 3, climate began to warm. It began to dry out. It was drier than present, but that was seasonal. You'll recall I mentioned that Washington has seasonal precipitation, and there must have still been a decent amount of winter rain, because there's a high abundance of ulmus rubra, which depends on a decent amount of winter rain. Also, our pteridium, our evidence of an open canopy, stops mid-zone. This is viewed as likely just the effect of the fact that pteridium is basically a pioneering species. As the forest matured, the canopy closed, the pteridium died out. it had high fire frequency. Regionally, this is similar to observed trends in the local study. There was warming and drying. There was generally observed aridity. There's a debate over how much. Kunar, who I mentioned before in that study of the West Cascades, suggests that a minor increase in aridity could lead to a tipping point, which would cause a major increase in fire frequency. But others dispute this. Some studies do record very high fire frequency or open canopy. Almost rubra can be used as a proxy for both, and so abundance of pteridium and charcoal abundance are also needed to separate out one signal from the other. This particular zone had a widely varying duration and initiation. As I mentioned earlier, depending on the site in question, it started anywhere from 11 to 8,000 years ago and ended anywhere from 8 to 3,000 years ago. During zone 2, there was an increase in moisture and a slight cooling effect was observed. Fire frequency decreased, and there was also, as mentioned, that significant fluctuation in thuya, tsuga, and pseudotsuga. So, trying to figure out what's causing that fluctuation, I thought, we don't have evidence to support fire frequency. There isn't a lot of charcoal, generally speaking. But what about fire intensity? And this is actually supported by other research. It's generally noted that in a seasonal regime, if you have wetter winters, you're just going to increase the biomass available for ignition in dry summers. Unfortunately, actually analyzing the charcoal data rejected this hypothesis. So here we have a graph of charcoal and thuya abundance, where abundance is calculated as the y-axis, with greater abundance toward the top, and sample number for depth is calculated along the x-axis with greater depth towards the right. So looking at zone 2, where our fluctuations occur, we see cases where the charcoal and thuya abundance peak at the same time. We see cases where the thuya abundance peaks right at the low point of the charcoal abundance. And we see cases where thuya abundance peaks and charcoal abundance isn't doing much at all. So, unfortunately, not really a good tie between the two data sets. So, what's causing the fluctuation in zone 2? I don't know. That's a great avenue for future study. Regionally, increased moisture was also observed. Cooling was observed actually in a stronger signal than was seen locally. Fire history varies dramatically between sites. In fact, a cursory examination of the sites will show that fire history seems to be doing so many different things that it's actually hard to figure out what's going on. Fortunately, it was complicated enough to promote a meta-study. And the average result of that meta-study was that fire frequency was initially high and declined throughout the region, throughout the zone. In most studies, this zone represents modern pollen, modern climate. Or at least modern before Europeans came along and burned everything to the ground. But as I mentioned, we had massively increased sedimentation in Lake Louise. So this allows us to tease out a fourth zone. And in it, a mild warming was observed, and a complex precipitation record. By this I mean we have 3 different plants that serve as a good proxy for precipitation. We have thuya, tsuga, and almus rubra. Thuya increased. Thuya decreased. Tsuga remained unchanged. Alnus rubra increased. So overall thought is that there probably wasn't much change in the average, but there was probably a lot more seasonal fluctuation than normal. Fire frequency was at its lowest during this zone. Regionally, while we don't see other studies breaking this off into a separate zone, we do see them showing what individually look basically like blips in the data. But these blips are all trending in similar directions. For example, Leopold, 1982, records a decline in cedar type, of which Thuya is one, and an increase in alder, or alnus. McLaughlin and Brubaker record an increase in alnus, a decrease in cupressaceae, of which Thuya is one, though they specifically noted there wasn't actually much Thuya in this particular study, and a slight increase in Tsuga. So some of these sites do suggest cooling, as opposed to the warming that I saw. Most of the sites that suggest cooling in the late Holocene are actually high altitude sites. Some do see increased sedimentation, generally not to the same degree. And generally, they're just of insufficient resolution to warrant more than a sentence or two in these papers. So, in conclusion, we had the terminal Pleistocene and early Holocene, a cold period experiencing warming with very frequent fire, the middle Holocene, warmer, drier, still frequent fire, and the late Holocene, slightly warmer and increased sedimentation. And I'd like to thank my advisor, Pete Van de Water, my committee members, Mathieu Richaud and Bob Dundas, friends and family for being here today. Questions?
That's a really neat study. Thank you for presenting that. It seems like Thuya might be the worst proxy for fire. You want to use alnus or sedimentation, or if there are, if there's aspen in the region, would this be a better proxy?
Absolutely, Thuya is not really a good proxy for fire, and I didn't use it as such.
Oh, you were comparing it. You were trying to correlate the ups and downs in region 2 or zone 2.
Right. But in this case, Thuya, alnus rubra, and pseudotsuga were all in flux, and Thuya recorded the greatest individual magnitude of flux. If you see
So
here.
it might tell you the wrong, it might have the right magnitude, but it might have the wrong frequency.
If you look here, they're all actually showing the same frequency, though.
But alnus, wouldn't that be the best one to indicate fire? It's your pioneer species.
It would absolutely, but alnus isn't doing anything during zone 2.
If you go back to the correlation between the two, where you're comparing Thuya to the charcoal. So could you, when you're looking at that, do you see like at first in zone 4 and zone 3 it kind of correlates a little bit better, then it starts to get out of whack in zone 2 and in zone 1 it anti-correlates?
One does see that, certainly. You can see some good correlation in this spot. You can see a little here, not as much in zone 1. You can see some correlation, or in zone 4, sorry. You can see some correlation in zone 1.
How about your high sedimentation rates in zone 1? Wouldn't that lead you to conclude the opposite of what you thought, and that is that you have higher frequency of fires?
Well, actually, Gita Dot in 2012 gives us the answer to this. And our increased sedimentation rate here is most likely due to increased organic matter. So this is a graph of weight loss on ignition, with weight percent increasing towards the right, and depth from 4 increasing towards the base. And you can see that more and more weight is being lost as we ignite this, which is more and more organics being lost.
How is that not biogenesis?
Or I guess, how is the organic matter and sedimentation related? What's the idea?
The idea is that these organic components are dying, they're excreting, and they're falling to the base of the lake.
So they're contributing to the sedimentation.
Right,
So they're what? What's the?
Contributing to the sediments? So
right.
they are sediments.
They are directly contributing to the sediment by becoming a part of it.
I still don't get it. If you had a big fire, then you wipe out all the cover, and I would think you'd have sediment flooding into the watershed,
Sure,
and would pick up a lot of organic matter too.
sure, that's certainly a possibility.
So I'd say high fire frequency at the top.
But there's a low charcoal frequency in the charcoal count. Yes?
Can you think of a reason why increasing sedimentation rate would cause you